now. So hello everybody to our Tech Talks at Rocket. Today we will present the outcome of the project SkinBall. But first of all, let me shortly introduce Rocket itself, Rocket Reloaded. Wait, wrong. Okay, Rocket Reloaded is a Cascade funding project within the Interreg 5A program Interreg Deutschland-Nederland. That means that we were able to finance several innovation projects, which can be seen on this slide. The main goal of Rocket Reloaded is to stimulate developments for innovative products and services that were possible by advancements of the key enabling technologies. Secondly, the project aims at the stimulation of Dutch-German cooperation in the border region. In general, Rocket Reloaded is coordinated by 4 core partners. On the Dutch side, we have OostNL. Also attending this meeting, Alex van Geldrop, from the lead partner, OostNL is the lead partner, and Holland Semiconductors. And on the German side, we have the Nano Micromaterials Photonics.NRW state cluster, that's we, in short, it's NMWP.NRW, and the Transfer Agentur Fachhochschule Münster. Over that, the associated partners are Novelty, Innos GmbH, and the Development Agency of Brabant. So again, together we were able to stimulate finance the 6 innovation projects in front of you on the screen. So within these Tech Talks at Rocket series, we want to introduce the outcomes of the innovation projects and the teams behind them at the end of the respective project. Nanoprint Pro, SensiChip, and Automess 3D were already presented. And the videos can be seen on our website, rocket-innovations.eu. And the last set of outcome of the projects will be nano-xenoscale and pure forensic DNA profiles, which will be presented in the future. But today, we talk about the project SkinBall, and our guest is Vitaly Rymanov from the lead partner Microwave Photonics GmbH. Within SkinBall, a hand scanner for the detection of skin cancer was developed. And yes, just a small remark, questions can be asked after the presentation in our discussion and networking session, and you can post them also into the chat if you think that you might forget them. But now, dear Vitaly, I will hand over to you and the screen is yours. I will stop my sharing and you can start yours.
Yeah, I will try.
Yeah, looks good.
Okay. Henry, can I start?
Yes, you can start. The screen is yours and the attention as well.
So Henry, thank you for the kind introduction. My name is Vitaly Rymanov. I'm from the company Microwave Photonics that is actually coordinating this innovation project called SkinBall within the Rocket Reloaded program. And yeah, I'm here to present the outcomes of our project. So here we can see the outline of the presentation. First, I will start with the key facts, motivation, and the vision of the project. After that, I will introduce the core partners and the subcontracted partners and the roles within the project. And then I will continue with the work packages and the outcomes out of these work packages. And finally, I will have the conclusion and the outlook. So let me start with the key facts. So SkinBall stands for skin tumor detection by using a millimeter wave photonic spectroscopy system. SkinBall is an innovation project financially supported by the European Union and the Interreg partners within the Interreg VA program Rocket Reloaded. So the core partners are Microwave Photonics, GmbH, and Mintris BV. Microwave Photonics is from the German side and actually the project coordinator, and Mintris is a second main partner. We have two subcontracted partners. There's the University of Duisburg-Essen and University Hospital Essen. So the duration of the project was 2 years. So we started in January 2020 and ended in December 2021. So what was the motivation for this project? The motivation was to support clinic facilities and practitioners for or in early skin cancer detection. So the vision was to realize a mobile instrument and system for simplified human skin monitoring. In the way you can see it on the reenacted scene on the right. So you see the patient, you see the doctor is holding a small instrument and investigated the skin of the patient. Here you see the overview of the work packages. In some we have 5 work packages, including 15 milestones. So the first one was about management, the second about SkinBall system design. The third one, SkinBall technological developments and packaging. The fourth, SkinBall instrument packaging and system integration. And the last one, the fifth one, was proof of concept validation, exploitation, marketing, and dissemination. On the right, you can see how the execution was performed in this project. So let us start with us, so the Microwave Photonics. So we were responsible for the outcome of the SkinBall prototypes. This means the instrument, the SkinBall system. We were providing designs, chip design, system designs to the University of Duisburg-Essen. The University of Duisburg-Essen was responsible to provide fabricated indium phosphide chips to Mintrus for integration with heat spreaders for improved thermal management on chip. So after that, Mintrus was responsible to provide this chip on carrier devices back to Microwave Photonics. Microwave Photonics was at the same time supported by the University Hospital Essen by providing skin samples and medical expertise for image analysis. In sum, we had 3 runs, as you will see on the following slides. Let me start with some photographs, or to remind how it was before maybe this pandemic situation of COVID-19. So this was at the same time the closing event for Rocket, where all partners have been contributing with a SkinBall poster and a SkinBall booth. But at the same time, it was also the kickoff, so the opening meeting for Rocket Reloaded, where all partners presented their new innovation projects. Officially, the SkinBall project kicked off in Oberhausen, Germany on the 7th February 2020. So all partners came to Microwave Photonics. Unfortunately, this was also, due to the COVID-19 situation, the last in-person meeting. So after that, we had lots of virtual meetings, telephone conferences, including technical meetings for modeling, including design simulation, fabrication, measurements, etc., medical meetings. But this is how it is nowadays. And device delivery meetings to organize the device transfer between all these partners we have. And finally, progress and status meetings. With respect to this, all of 15 milestones were done on time within the entire project time from January 2020 to December 2021. Let us come to the specification. So as we are talking about the millimeter wave application or n millimeter wave application for the instrument and the system to be developed in this project, this specification for the SkinBall system were defined within the Ka band. So which means it was the K band starts at 26.5 gigahertz and ends at 40 gigahertz. So this is the same also the band for the waveguide standard WR28. So you will get to know more about this standard or about the application of WR28 devices in this project. So with respect to the skin and skin cancer, especially for skin cancers and non-melanoma cancer, we put the focus on a special property, and this was the permittivity. Getting more used to get to know about the properties of, or the difference between skin cancer and skin, you can see in the figure on the left that you can identify stable difference in the permittivity of skin and the permittivity of the skin cancer starting from 30 gigahertz. So it's almost stable. Additionally, you can see that skin cancer is not only skin cancer, so you have to differ for non-melanoma skin cancer between SCC, so squamous cell carcinoma, and BCC, basal cell carcinoma. And to see also the properties or the permittivity differs slightly, only slightly, for BCC from the permittivity of skin, and there is a more clear difference between SCC and skin permittivity. So we put the focus on the SCC to have a statement and to have a clear outcome of our investigations. In addition to this, and as it's not usual to get these skin samples day by day, we also investigated skin mimics, which are skin phantoms pretending the properties of a skin tissue. So we were able to design and fabricate these mimics in the lab and use them instead of skin. So first, you can see the Photonic K-band sensor concept on the left. And in addition to this, the prototype developed in SkinBall on the right. So first, looking at the concept, you can see that this sensor includes a photodetector on top of a 3-port circulator. On the right, we have a probe antenna for transmitting and detecting an RF signal to our device under test. And on the left, as a detector of your reflected signal, you will have a Schottky barrier detector. So in analog to this concept, you can see the realized device. So you can see the photodiode right here. You can see the probe antenna right here. You can see the 3-port circulator between the photodiode, the probe antenna, and the connection to the Schottky barrier detector. Having this sensor, we were aimed at a calibration of all single devices, at least up to 40 gigahertz, but also partly up to 50 gigahertz. So also covering the Q band, so-called Q band, starting from 33 gigahertz up to 50 gigahertz. As you can see, the PD module is providing a quite flat frequency response. from DC up to 50 gigahertz. So it completely covers our range of application. We are still within the 3 dB flatness. And the key factor here, the maximum power required by the detector, the Schottky barrier detector, is finally at maximum of minus 20 dBm. So this means that there is only a photocurrent of 1 up to 2 milliamps required to achieve this power before the detector, the Schottky detector, starts to saturate. We did the, and this is why I mentioned here, also in addition to WR28 standard, also the WR22 standard, which relates to the Q band up to 50 gigahertz. We use a Schottky barrier detector for WR22, and we're able to go down to the lower cutoff frequency and up to the highest upper cutoff frequency of this waveguide standard, and we're able to extend the Q band down to the Ka band, so down to 26 gigahertz, and fulfill the top frequency at 50 gigahertz. But nevertheless, we have two limiting components, and these are the pure mechanical WR28 circulator and the probe antenna. So the we were looking also for circulators operating at higher frequency, but this was the only one commercially available. So this limitation is in the system. The probe antenna is a pure mechanical device, so it operates like the circulator. So as a conclusion, these both components are the components that are limiting our current photonic sensor. Well, as I talk about the heat spreader integration, here you can see the concept plan we developed within the project for the PD integration and for improved heat dissipation and distribution within the hotspot of the photodiode. So as a material for the heat spreader, we use a chemical vapor deposition, so short CVD diamond. So it's synthetic diamond material. There was a AutoCAD design made for the reframe mask made, fabrication done on this, and dicing of the heat spreader. So you can see on the right, right here, the fabricated heat spreader to be used for the hybrid integration on the photodiode. Here you can see the AutoCAD design covering both. So here in the middle is the heat spreader on top of a vertically integrated photodiode. For bonding, we use thermocompression bonding. The concept of this one is shown here on the right. And you can see we had different concepts. So to introduce a photodiode on top of the heat spreader, to introduce the heat spreader on top of the photodiode, referring to this, also the designs of the heat spreader were matched. So you can see from this one, you can go for on-top illumination through your heat spreader. From this one, you can go through the bottom of the photodiode and reflect at the bottom of your heat spreader back to the photodiode. What we can see here is a developed photonic assisted cable imaging system. On the left, we have the concept, and on the right, the prototype we used also for our final measurements with skin samples. So let me introduce and explain first the concept, but maybe at the same time also the realized prototype. So we have two tunable lasers, 1 and 2. These are connected by a 3dB optical coupler. They're connected to get out a heterodyne signal to be applied to the photolite at the millimeter wave signal. So having the optical signal at the photolite, you're converting which maybe on the right, you can see it here, this tunable laser box, including 2 lasers. You see the connection by the 3dB optical coupler. And then you're going to your sensor right here. And as already introduced, the sensor, after the OE conversion in the photolite, is guiding your RF signal to the probe antenna. The probe antenna is in contactless distance to your device under test. So here at the beginning, we used as a perfect reflector coin, I think it was a €2 coin. You can see it also here within the system. And then your reflected signal is going back through the circulator and is transferred to your Schottky barrier detector. So the data received by the Schottky barrier detector can be shown as a 2D imaging figure here. After this first test, after we get used with the first test, we started validation test using different materials to see the applicability of the photonic sensor in the system. We used acrylic glass, we used wood, but the key material here is agar-agar. So agar-agar is one of the ingredients of the skin phantoms. I will show you on the next slide. And as you can see, referring to agar-agar, your contact distance was defined at 0.4 centimeters. Here on the right, you can see the 2 recipes for a potential skin phantom design. We use the bottom one, so the gelatin phantom, including only 3 ingredients, but delivering almost the properties. Almost means it's not on point, but it's almost similar to the skin permittivity or the skin refractive index. And we got the refractive index measured around 4.25, which is slightly different from skin, depending on your frequency. But at this frequency range, there was a slight difference to 4.6 for skin and 4.25 for the skin phantom. But having the skin phantom, you're just able to measure the property of your skin, which you can see here. But to see, is there something malignant within skin, you need also some skin cancer phantoms. There's one way to get a further phantom working, which is getting quite complicated, to get the difference in the permittivity between the skin phantom and the skin cancer. But if you can handle it in a way that you're finding something similar, providing a similar difference in the refractive index to your skin, you can use also silicon, because if you look on silicon, the difference between silicon and skin phantom was finally something about 1, but lower by 1. If you look on the difference between skin phantom and skin, and the difference between the skin cancer and skin, it's about also 1, but higher than 1. So finally, if you are getting your imaging to the imaging figure, you will see the difference plus or minus 1 will be the same. So why we introduce these areas of the silicon samples? So it's somewhere between 2 and 10 millimeter in diameter when you're recognizing that there is a cancer in early stage. So the aim was to see the resolution of the system and to identify how small can the samples be to be identified by our developed system. Here in between, you see different designs of the developed photodiodes. We have 2 designs for the vertical photodiode. This one on the left here, you can see the first design. We produced test samples on this to get started with a heat spread integration on dummy photodiodes, and then we fabricated hot ones of this, and finally in parallel we also were working on a waveguide approach to get a more cascaded way within the packaging process. So not to have the fiber on top of the package, so to have it more on the side. So incoming fiber would be cascaded with a waveguide photodiode and then cascaded with a platform to be connected to the photonic package. So here on the right, you can see the optical characterization. On the left, the RF characterization of the fabricated photodiodes. Here you can see some thermal simulations we did, and just to show you and demonstrate what is the impact of this heat spreader when it's integrated with a photodiode. What you can see on top, you can see the heat spreader. So you can see it here, or you can see it here, you can see it here. Here you can see the substrate, and here you can see the substrate of the photodiode, and in between you have the hotspot, so the active region of the photodiode meson. Applying 300 milliwatts of thermal power within the simulation to the hotspot, you can see a huge difference between a device having a heat spreader or not having a heat spreader, and the temperature difference is about 286 Kelvin. Which means for a long-term operation, this would not be the best option to be used at higher operational power without having a heat spreader. Here some more details on the heat spreader integration with the photodiode. Here you can see again the concept, so having the heat spreader on top of the photodiode. We have design and fabrication already presented for the heat spreader, and then after this we came to the vertical photodiode integration with the heat spreader. So you can see the alignment, or after the PD dicing, there have been tests on the alignment. So alignment was done quite well, having an alignment accuracy of ±1 micrometer. So you can see through the microscope here. And finally, the TC bonding. Here again the concept, and the photograph of a TC bonded photodiode together with the heat spreader. You can see slightly the shape of the heat spreader here, and below this, as the heat spreader is transparent using the diamond, you can look through the heat spreader and can see the metallic contacts of the photodiode. The next one, as I already mentioned, to have the chip inside your photonic package, you need also the connection between your indium phosphide chip and your WR28 output. So for this, you are requiring a GCP-W, so grounded coplanar waveguide, to WR28 transition. That is introduced here. You see the modeling in the middle of the slide. And this one includes, in addition to your transition, which would start, I mean, the RF transition would start here when you're positioning here your photodiode at port 1. And here at the double slot antenna connected, here at the lower stage, you can see the output of your rectangular waveguide. So this means you're still requiring some biasing for your photodiode, and your photodiode will be biased by this channel here. This channel is for DC biasing to photodiode, but blocked, having a DC block right here and RF choke right here. So this means only the DC signal can propagate this way, and only the RF signal can propagate this way. Here you see the fabricated devices. So this one we will see further on in inside the package, and this one was for prepared for end launch connections to get some network analyzing on this without any integration. Here we're getting closer to the package device, and here the two modeling figures on the pure photonic package. On the left, you see the covering plate, just close your package, and on the right, you can see the package, the photonic package, including the input for fiber input. You see 4 holes for DC pin connections, and you see also this hole for your WR28 output. So to make it work, now you're requiring the integration of your single components. So this means you're requiring optical fiber. So the operational wavelength was at 1.55 micrometers, if not introduced on the previous slide. We use a waveguide photodiode from round 3, as already mentioned, to have a cascaded approach inside the package. We use four DC pins introduced in the holes of the package right here, and the integration platform, connecting by wire bonds to the photodiode and to the DC pins. If you're wondering why we have 4 DC pins, if you remember the design of the photodiode, the third run photodiode includes 2 photodiodes. There is a Photolite Array, and this means both are connected by an optical coupler or splitter. There are 2 different versions of this one. So one 50-50 one was more, so 50-50 optical coupler was used for tests. So you can do at the same time the test on a heat spreader integrated photodiode, and at the same time on the non-integrated heat spreader photodiode, and see what is the difference between both fabricated photodiodes. The other one, and this approach was introduced in the package, was we are having a 25 to 5 optical splitter, which means that 25% of your RF signal are going to the main channel here and are radiated through your photodiodes, and the other one is going to the second channel, which is only for DC biasing of the second photodiode, and to see how the polarization, the optical polarization state of your photodiode is. So both are connected by this special optical splitter, but by biasing both, you can see also the polarization state of your hot photodiode. You see the dimensions of the entire package, and it's also fully integrated, shown on the right side. It's about, the length is about 4 centimeters, and the height and width somewhere about 2 centimeters. So it's quite small. And we have all the devices introduced, all the devices before the circulator introduced in the previous slides are now inside this package. So you can directly connect this package to the circulator, the probe antenna, and the Schottky barrier detector. Well, let me now present the first system validation and measurements on the skin cancer mimics. So as I already introduced, we fabricated these skin phantoms here inside a plastic box. We positioned the gelatine kind skin phantom inside the silicon samples, and get the 2D image, as you can see on the right, of the sample using our SkinBall system and sensor. It can be clearly seen that the device having 1 × 1 square centimeter right here can be observed in this 2D imaging. It can be also clearly been seen that the 6 × 6 millimeter square millimeter sample can be seen here. But as you can see, getting for a smaller device in the range of 2 × 2 square millimeters, it's getting challenging. So the outcome of this was that we are able, as you can see, this 2D image is based on the refractive index of the measured refractive index. We are able to detect a complex refractive index magnitude difference of higher than 0.4. And we are able to detect samples within the resolution or spatial resolution of 5 millimeters, or of a minimum spatial resolution. So samples are larger than 5 millimeters in diameter could be detectable by this system. Samples like the smallest silicon sample are getting challenging. So here was again what was already mentioned on the previous slide. You can see the difference of your BCB to the surrounding skin in the refractive index, and the difference when you see here the surrounding skin of SCC, you are by 1 higher for the SCC. Here I come to the final measurements, and these final measurements were done using the provided skin tissues and SCC samples from the medical side. And this was quite challenging. You know, it's not the same as for a piece of silicon, which is quite planar and can be smoothly embedded within the gelatin of your skin phantom. You are not able, or at the beginning it was not able to put them in the right position. You were running out of time because also the skin at air is starting to dry out. And finally, we found a solution to give these samples a raw cell surrounding or background, which means that the epsilon R of raw cell is comparable to air. So we are looking on these samples like we're looking on these samples somewhere in air. And we're just focusing on the properties of these two samples, completely neglecting the background. We're using again the frequency of almost 39 years. Maybe I didn't mention yet, but why 39 years? Because this was the highest isolation given by the circulator. And just to get the best out of the system, we used this frequency to operate within this highest isolation given by the isolator to get the pure signal provided to the Schottky barrier detector. From the literature, the refractive index of SCC skin tissue is on average about 20% higher than the one of the healthy skin. The big issue here was to find a skin tissue and an SCC sample that are comparable to each other. We received diameters or similar diameters in the range of 4 millimeters, but the thickness was different. And to implement both in raw cell, having the same height for measuring without any mismatch to your measuring distance to your probe antenna was a quite challenge. So we are not working on the medical side usually, so handling the human skin tissues were not that usual for us. And but finally we managed this, introduce them to raw cell, and considering the amplitude measured on this and considering that the diameter was below the expected minimum spatial resolution, we could already see the difference between the SCC sample and the skin sample. Just to give a number, the amplitude difference was about 0.4 millivolts between both tissues, and the conclusion was, this was right at the end of the project, that in any way having more measurements to be done on this, we require not only separated skin and SCC sample. In the best case, you're having a SCC sample with a minimum diameter of 5 millimeters, surrounded by an additional 5 millimeter of surrounding skin, which is not usual because we are still talking about human skin and human tissues, and this is not a, let's say, Wunschkonzert in German. And so for the future, to get more use from measuring skin samples. There are larger diameters required to be provided. And in best case, also, we need some uniform samples to have a comparable measuring, like having a patient having skin, and within the skin you are having some kind of malignant SCC cancer. Based on this characterization and validation, we got for the first step the measurements on the skin phantoms. So we got the first medical applicability report and the approach using some skin cancer and skin phantoms was very welcome. And this way we were greenlit by the medical side just to go for the next step and use human-based skin tissues and skin cancer tissues. And with respect to the results shown on the last slide, basically, and I can read what was written in the report, basically it can be stated that non-invasive contactless imaging for screening for the presence of tumors would be great potential, which for sure require a database or valid data collection of not only a limited number of SCC samples, which only could be provided within the project time we had, but also for some future activities. This is the next target and the aim to build up a database collecting more measurements on provided skin tissues and then have a medical evaluation based on all these results. To summarize maybe some figures on the publications and reports we had within the entire time of our project. So we had 3 papers, 2 scientific works. So these were also dealing with the design and fabrication of the skin phantoms. We have 15 conference, exhibition, and event contribution, 17 press and web releases, and finally more project internal, but 2 medical applicability reports, 3 progress reports, and 1 final report already submitted. Then we come to the conclusions. What are the outcomes of this project and what are the innovations? So the outcomes are sub-products and products operating within the range from frequency range from 26.5 up to 40 years, all developed in this SkinBall project. So these are the K-band Photolite module, so also integrated in the module. The K-band RF transition and photonic packaging, looking on them as a single or pure mechanical devices, but quite helpful for photonic packaging. Photonic K-band sensor for skin cancer detection. And finally, overall, the photonics assisted K-band imaging system, providing the first 2D imaging on skin phantoms, including some skin cancer mimics, as well as first measurements on the skin tissues provided from the medical side. What are the positive outcomes from SkinBall? For sure, and after all collaborations within this project, there are new partnerships also for future collaboration. as I already mentioned, with the medical side, we are still in contact to get to increase this database, including some measurements on the human skin. All of the partners gained medical expertise in dermatology. I think not all of us were that familiar with this medical side before SkinBall. So we provided new solutions for RF and photonic packaging. We provided new solutions for in-patch thermal management. Here I'm talking about the collaboration with Mintrus. And the photonic sensor and system development is leading, or was leading, to progress in early skin cancer detection, also commented by the medical side. For the outlook, so the connections, what are the connections with partners? I already mentioned this. So the new sustainable connection is between the German partner, so Photonics, us, and the Dutch partner, Mintrus. So also for upcoming packaging and in-package thermal management activities. There is still collaboration with the German partner, University Hospital Essen, with respect to medical expertise, and some further upcoming projects dealing with terrace range to improve the resolution of the system. And this also, when I'm coming to the basis for future activities, or some further future activities, and talking about closer collaboration with the University of Duisburg-Essen and the University Hospital Essen. There are already plans for future projects for development of terrace near-field scanners for the medical sector. So increasing the resolution to get closer, also for smaller sample detection. And in general, this project also demonstrated a radio fiber system for K-band application, and not only for the medical sector, that can be extended and can be exploited also for application in the test and measurement sector, space sector, which is quite usual for the cable. Yeah, this was my last slide. I would like to thank for your attention, and if there are any comments or questions, you're welcome.
Yes, Vitaly, thank you very much for your interesting presentation. Yes, we have the first hand is raised from Matthias Grosch.
Yes, thank you very much for the interesting presentation. I'm not sure if you maybe mentioned it. What is the amount of energy that is radiated towards the skin? I mean, if we have a certain frequency of radiation going onto a living patient, that's always, I think, a security issue. Like how high or low is the radiative energy you use?
Yeah, let me show you something. Maybe I can show you the figures on the radiation, or the power we used, or the output power from the sensor was around, it was lower than minus 20 dBm. So the limitation was not given by the, or from the medical side, the limitation was at least given by the Schottky barrier detector, which is saturating when you're getting higher than minus 20 dBm input power. So this is this the answer for your question?
kind of what is the, do you know what the medical the region of power to the skin is there in this regard? Is it much so is the medical limit much higher than this, or?
Should not be, because here we are at quite low input power, so I can give you a right figure, or the correct figure, or the precise figure to this. I can come back with this question to the medical side, asking for this.
Okay, I mean, I understand it's quite a low amount of power, so probably.
Yeah, for sure. But if you're asking for a precise number,
no, just more of the relative. Is it? It seems it's below the medical limit.
Yeah, for sure.
Okay, thank you very much.
Yeah.
Okay, I have another question in the chat. So you use 2 lasers to generate an RF signal in Ka band. Ka band, yes. And the reflected microwave is measured with a diode detector. So how do you scan? Mechanically or by moving the instruments? Since smaller than 40 gigahertz is the range of electronics, why do you generate the signal optically? Is the pulse power so large?
What is the first question?
The first question. Okay. Okay, let's begin with the question. Yeah. So you use 2 lasers to generate an RF signal in Ka band, and the reflected microwave is measured in a diode detector. That's right?
Yeah, IF. Yeah, you're getting IF.
Okay. So the question was, how do you do the scan? Mechanically or by moving the instrument?
You mean the measuring here at this point?
Yes.
Because by moving means what we are doing, we are moving the sensor, or we are moving the stage. So if this is a question, we are moving the stage in the X, Y direction, and we are moving the sensor in the Z direction to get the right working distance.
Yeah, okay. Because I think there was another hint in the chat. The 2D image, how is it obtained? But I think you answered the question already. Okay, so the movement. So this is okay. Yeah, and then the next question was, first of all, G. Grau, what is the first part of the question answered? If possible, or if you want, you can also activate your microphone. Maybe this is a bit easier.
Might get easier. I don't know if my scope in the background is too noisy. Yes, I think the first part has been answered. So since my background is microelectronics up to the terahertz domain, my question is why did you use this kind of optical mixing to generate the 40 gigahertz?
I understand this completely. Yeah, you see, as I already mentioned, this project works as a pre-project for follow-up project for the terahertz range. So if we start the development within the terahertz range, we have to demonstrate that the concept is working.
Okay. Yep. So for the time being, my questions are answered. Thank you.
Fine.
Okay. So perfect. If you have further questions, just type them into the chat or raise your hand. Matthias again. Matthias, you have another question.
If I may, thank you. I have a question. So you're using for the thermal spreading CVD grown diamond film.
Yeah.
Is the film produced on another substrate and transferred, or is it grown on the?
No, this is a hybrid integration. So let me show you this one. So the approach is like this. So you are fabricating the photodioide first, and at the same time you are fabricating diamond platform, which it depends on your approach. You can use it as a platform, or you can use it as an on-top device for your photodiode. And then you're using thermocompression bonding, using gold pads in between, and then you can also manage to get over this height difference in between.
Okay, maybe a follow-up question. Has there been the idea to use another material that could be maybe on top instead of the diamond?
Yeah, but we were thinking about this. Also, diamond is not the cheapest one, but the advantage, especially for us, was to have a transparent material like diamond. And our partner Mintrus is quite used with applications using diamond, and this was the reason. All the technology was provided by Mintrus for the hybrid integration, and they were prepared to use diamond on top, on bottom of the photodiode, and especially to have it on top. Especially for the alignment, as you can see here in this figure, to get that precise, or to get the accuracy of ±1 micrometer, you have to see through the microscope both devices.
Okay, yeah, I see.
Yeah.
Okay, thank you.
Thank you.
Okay, thank you.
Welcome.
In the end, I think the project has proven that the technology is suitable for skin cancer diagnostic, which is very interesting because it's also suitable for 6G, as far as I know. But so I think you have achieved your goal. But what limiting factors were you able to identify in the project? For example, the resolution, because I think I saw that you mentioned a tissue of at least 5 millimeters. So what about smaller skin cancers, because you're talking about early detection? What should be improved?
Anyway, we have to go for higher frequency. So the resolution and the technology, as I already mentioned, this waveguide standards, we can see the table, are getting smaller with your frequency band.
Okay.
So this means your sensor, your probe antenna will get smaller, and this all about the resolution you're getting for the terahertz range as expected, and then you will be able to receive also smaller spatial resolution.
Okay, and therefore you need new components, I guess, which are, I think, as are they available? For a higher frequency, do you have to develop completely new?
For higher frequency, looking on components like the circulator, these are not off-the-shelf components. So these will be, at least one work package within the project to be developed.
Okay, great. And another question I have: how long will a measurement process take in practice in the end? Because you said, okay, I think it might get hot, if I'm right, if I interpret it right.
No, it should not get hot.
Okay.
This hot effect was only the active region of the photodiode.
Okay.
out of the, and for this, and it depends also on the applied output power, but at this power level, nothing is getting hot. And
how fast is your innovation?
It takes, it depends on your scanning steps, but for the time being, it was about I would not say it. For sure, depending on the area you're scanning. It's not for a line scan. Just to identify what is skin and what is tissue, it would take about some minutes.
Okay, so it's quite fast. Okay. much
But
faster than
for sure. But for sure, if you're looking for the entire region and you need an entire 2D image of your device under test, this takes some more runs of your scanner. And then line by line, you will build up your 2D image.
Okay, and how large could the area be that you scan one by one time at one time?
Yeah, but this you mean using this system? Because this
Yeah,
system,
yeah, or also
because
in the perspective, because I understand.
Usually,
okay, you need a
yeah.
bigger, a higher resolution, so
Yeah.
a higher frequency.
Yeah, for sure.
But it's a mobile device, and
Yeah.
how big is the region you can scan one by
when you're
one time?
using it really as a mobile device, there is no limitation, because you can start wherever you want and you end wherever you want. But using this system with a fixed XY station, it was about, let me give you a number. We can see it here right now.
The euro.
Yeah, the euro can be seen, so this comparable, but also from this figure, it's
this is
about,
quite big.
Yeah, it's something about 4 or 5 centimeters.
Okay, okay. Yeah, that's great. So, do you have further questions? I think until now there are no further questions. You already mentioned this is something. It's rather a pre-project for further developments. So I think maybe it's a good idea to keep an eye on this, and maybe there will be follow-up projects. Surely. Okay, so we made a screen recording and we plan to publish it. So as soon as we did this, we will send an email to all of you, so you can have a look at the presentation afterwards. And if you have further questions, you can also ask them afterwards, either to us or to Vitaly directly. If it's okay, I can provide the email address for further questions. And yes, so as there are no questions, I would like to thank you all. Vitaly, thank you for the presentation, and to all the participants for the questions and the interest in this project. Thank you very much. And I hope we will meet again soon in other projects or webinars. So see you soon. Have a nice evening and bye-bye.
Bye. Thanks.